Hello! In this video, we present the retrosynthesis of Levetiracetam, isotopically labeled with 4 tritium atoms. This isotopologue can prove to be useful in the investigation of both the pharmacology and the metabolism of this anti-epileptic drug. In general, this retrosynthesis begins by disconnecting 2 vicinal carbon-tritium bonds. This process is based on a retroaddition reaction that occurs to a double bond, followed by another pair of carbon-tritium vicinal disconnections, which are based on substitutions. Subsequent transformations generate raw materials that are commercially available, as we will see later. And the primary source of tritium is molecular tritium. The retrosynthesis begins by disconnecting the 4 tritium atoms. First, a vicinal pair that is based on a reductive substitution. These disconnections generate elements which are then susceptible to being reduced, such as chlorine or bromine, leading to the formation of lactam-2, and molecular tritium, which is used as the source of this radioisotope. Next, the other vicinal pair of carbon-tritium bonds proceed to be disconnected by means of a retroaddition reaction to a double bond, leading to the formation of the unsaturated compound 4, and another equivalent of molecular tritium. The lactam group of 4 functions as a retron, and a carbon-nitrogen disconnection opens the heterocycle, generating carboxylic acid 5. A second carbon-nitrogen disconnection of 5, based on a substitution reaction, gives rise to the chlorocarboxylic acid 6, and the aminobutyramide 7. The 1,5 relationship between the hydroxyl group and the carbon bonded to the chlorine atom in 6 suggests the formation of a carbon-oxygen connection to produce the unsaturated lactone 8. A functional group transformation in 8 generates the unsaturated hydroxylactone 9. This hydroxylactone can be obtained through the oxidation of furane 10. 2 carbon-halogen bond disconnections in compound 10, where X can represent either bromine or chlorine, based upon an electrophilic halogenation, results in the formation of 2-furoic acid 11, where the carboxyl group, positioned at carbon 2, plays a role in controlling the regiochemistry of the halogenation when reacting with a molecular halogen, where X can be either chlorine or bromine. The amide group of 7 functions as a retron, and, based on a retroamidation reaction, a functional group transformation produces ester 13 and ammonia 14 as a raw materials. Another functional group transformation of 13 gives rise to amino acid 15 and methanol as a raw material. The amino group of 15 can be generated through the asymmetric reduction of the imino group of 17, which is itself formed by a functional group transformation. The imino group of 17 functions as a retron and a carbon-nitrogen double bond disconnection produces the alpha-keto acid 18 and ammonia as a raw material. A functional group transformation of 18 leads to the generation of the ethyl ester 19. The ethyl group, which is attached to the carbonyl, can be obtained from the Grignard addition reaction to diethyl oxalate 20, utilizing ethyl magnesium bromide 21, both of which serve as raw materials. In summary, here are the main disconnections. In the next video, the resulting synthesis will be presented.